Okay, next up is question number 4 on the worksheet. It says to find the volume of the ice cream cone bounded above by the sphere x squared plus y squared plus z squared is equal to 4. You see that up here in green. And bounded below by the cone, z is equal to the square root of x squared plus y squared. You see that here in blue. Notice also that this is the same question as problem number 4 on the section 14.3 worksheet. And in that solution, we computed the volume of this ice cream cone by computing a double integral. Now if we project this solid onto the xy plane, okay, we get a disk, and so we computed a double integral over that disk, and so we use polar coordinates. Okay, now in this solution we're going to go ahead and compute the volume using a triple integral, and we'll compute that triple integral using cylindrical coordinates. And we'll see that our solution winds up looking rather similar to what we did back in 14.3. Alright, so to begin, we'll first just note that if we call this solid, right, this ice cream cone that we're finding the volume of, E, then to compute the volume of E, we just want to compute the triple integral over the solid E of 1 dV. Okay, so to compute this triple integral, let's go ahead and let z vary first. And if we fix an x and y and let z vary first, so think about filling out this solid ice cream cone with vertical pillars like you see here in orange. Okay, we're going to let the z height vary from the height on the cone up to the height on the sphere. Now, since we're going to use cylindrical coordinates, I'm going to go ahead and rewrite the sphere and the cone equations in terms of cylindrical coordinates. Okay, so now given that x squared plus y squared is equal to r squared in cylindrical coordinates, z then for the cone is just r itself. And then for the sphere, okay, noting that we're looking at a portion of the top half of the sphere, solving for z, I want to use the positive square root, and I get 4 minus the quantity x squared plus y squared under the root. And as we just noted here, x squared plus y squared in cylindrical coordinates is r squared, so for the sphere height there, we have z is the positive root of 4 minus r squared. Okay, so for a fixed x and y, z will vary from the height on the cone, and that's just r, to the height on the sphere, and that is the root of 4 minus r squared. Okay, so now let's find the bounds on x and y, and to do that, let's go ahead and project this solid onto the xy plane, just like we did back in the 14.3 solution. And that's going to give us this disk in red. And I'd like to go ahead and find the radius of that disk. And notice that this boundary circle for the disk is the projection of the intersection of our sphere and our cone. Okay, so if I go ahead and set the cone equation and the sphere equations here equal, I get, right, that the radius r of this boundary circle is the square root of 2. So down here, right, I can describe this disk as the set of all points in polar coordinates where r varies from 0 to root 2 and theta varies from 0 to 2 pi. Okay, so those give us our bounds on r and theta, and of course, right, our differential area element down here in the xy plane when working with polar coordinates is r dr d theta, or put another way, okay, this all together, dz r dr d theta, that all together makes up the differential volume element in cylindrical coordinates. Okay, well now let's go ahead and compute the z integral. And so here, r and theta are fixed. And so I can go ahead and just integrate this constant 1, and that's just going to give us a z. And then when you evaluate that at the root of 4 minus r squared, that's just going to give you the root of 4 minus r squared, and then you're going to subtract from that r. Okay, so we just get the difference in these bounds, and then we have that factor of r outside parentheses in our dr d theta. And now, if we just take a moment to pause, we've seen this integral. This is in fact the exact same integral we got when we set up this volume calculation using a double integral back in section 14.3. Okay, so you might want to go back and review how we had set that up. All right, well, the calculation is just the same from here on out. Okay, we can go ahead, since the integrand here depends only on r, okay, we can peel off this integral from 0 to 2 pi d theta. That can come out front. And then here, if I distribute that r, I'm looking to integrate r times the root of 4 minus r squared. We can do that with a substitution. And then here I'm going to get a minus r squared. And if you carry that all through, just as we did back in 14.3, you wind up getting a volume of 8 pi times the quantity 2 minus the square root of 2 all over 3. All right, and that does it. Thanks so much.